Hi guys, it's Kate. I wanted to make this video to allow for a little bit more discussion on a topic that many students find challenging to understand. So my hope is that you're able to take advantage of the fact that you can rewind or fast forward or watch this as many times as you want until this concept of alternating series and their associated error bounds makes sense to you. Now in class, you learned the alternating series test for convergence. That's not what this video is about. Instead, we're going to take the next step and say, okay, maybe you have an alternating series that's convergent, but you're only using the first few terms of that alternating series. And your big question is, okay, if I only look at the first 4 or 5 terms or 6 terms or n terms, how far off am I from that sum, that finite sum? How far off am I from the value that the infinite series actually converges to? That's the big question. And the first way to look at this, there are lots of questions that you'll see on problem sets that deal with this concept and this idea. Some of them are saying, okay, you're only using 5 terms. How far off are you? At most, how far off are you? Or sometimes it says you want to be this accurate, how many terms should you use? You guys have some familiarity with that idea from our numerical error and integration unit at the end of the slicing unit. There are those, okay, you use this many slices, what's your error bound? Okay, I want this error bound, how many slices should I use? It's an analogous style of question. So let's talk about conceptually what's going on and then go ahead and solve some problems. Now, when we were talking about how series converge or diverge, one of the ways that we looked at this phenomenon in a more qualitative sense was by looking at a partial sum diagram. And we got really used to looking at partial sum diagrams for series that converge or that diverge. And the key characteristic for a series that converges when you're looking at a partial sum diagram is that the partial sums, as you continue to plot them on this number line, are getting closer and closer and closer to some point. Let's take a look at what that may look like. For example, on your worksheet, you did the alternating harmonic series. Let's throw this up on the slide. So here's a look at the alternating harmonic series, both sigma notation as well as writing out the first 6 terms. Now, we discussed in class why this is a convergent alternating series. Not only are the terms strictly decreasing, that means that each consecutive term is less than the term that comes right before it, but the terms limit their magnitude. The limit of their magnitude is also 0. So it satisfies the 2 conditions to be convergent as an alternating series, but of course, when you're looking at it and trying to go for absolute convergence, if you took the absolute value of each of these terms, you would actually have the harmonic series, which we know diverges. So this is a classic example of something that is not absolutely convergent, but does converge based on the alternating series test when you allow the signs to swap back and forth. And so we call this a conditionally convergent series. Now, when we look at what the partial sum diagram for this looks like, I'm not going to draw this very strictly to scale, but I'm going to give it my best shot. Let's throw down a number line here. And we will plot a couple of the partial sums. Now, I'm not going to go through and actually hard compute exactly which fractions correspond to which partial sums. Instead, I'm going to use the fact that I know that the next higher partial sum is different from the previous partial sum just by adding the next term. What do I mean by that? Well, I know that if I look at the first partial sum, which is just the first term, that's going to be right here at 1, because that's the first term. And then in order for me to get the second partial sum, rather than taking 1 and subtracting on a half and computationally on a piece of paper writing down, oh, that's 1/2, all I'm going to do is subtract 1/2, which is the second term, from the first partial sum, and I'm going to end up right here for my second partial sum. Then to get to my third partial sum, I want to add a third, right? I'm just adding the third term to get to the third partial sum. And I don't know exactly how big a third would be according to how I've drawn this, but what's important is that this distance right here was a half, so I know it has to be less than that. So when I go to plot the third partial sum, it's going to be about here, and that would be reasonably correct. Then I want to do the fourth partial sum. That requires subtracting off 1/4. Well, I know that from my previous drawing, this distance right here is 1/3, so it's going to be slightly less than that, and I'm going to maybe land about there. That can be where my fourth partial sum is. And then my fifth partial sum will be somewhere over here. And we see that as we draw more and more. Sixth partial sum. They are centering, approaching some value that's in this chasm. And we get an idea of where that value to which this series converges is. We get more of an idea, a better and better idea, the more terms that we add. But what's important is that you notice that every time we went to add on another term, what was happening? Well, the first time we added the first term, right, we went from 0 to 1, and it took us all the way here. It took us up and over the point of convergence here. Then when we subtracted off that 1/2 to get to the second partial sum, it sort of ping-ponged us back over whatever we seem to be converging to the other side. And this continues. Every time we're adding another term, and of course that practically speaking is either addition or subtraction because this is an alternating series, but every time we include another term in the series, we are ping-ponging up and over where we're converging to. So when we added the third term, right, we were adding 1/3 to get to the third partial sum. It overshot the value to which it converged, which we're unclear on what that is, but it does exist somewhere in here. When we then subtracted 1/4 to get to the fourth partial sum, it rocketed us back here. Adding 1/5 shot us over here, subtracting 1/6 put us over here. So what ends up happening is that these next terms provide great error bounds. Now, remind yourself what an error bound really means, right? When you have an approximation and an error bound, they go hand in hand. You don't just talk about error bounds out of context. You have a particular approximation. You're only looking at a part of the series, the first couple of terms. And you say, okay, I have this approximation and I have this error bound. You assemble that into a sentence and you say, my approximation is within the error bound of the actual value, right? That's what the relationship is between the finite sum that you're using when we're looking at these partial sums and the error bound that we are trying to search for here. But what's great with alternating series is that rather than go through a lot of computation to find what an appropriate error bound would be at a particular partial sum, they're actually quite straightforward to find. Because we know, for instance, say we only used the first 3 terms to approximate this entire series. That would mean that we were saying that the series is approximately the value of this third partial sum. What would be a good error bound? Well, because of what we know about how alternating series that converge behave, we know that by subtracting 1/4, we are guaranteed to land on the other side of whatever we happen to be converging to in the middle. And that 1/4 value becomes a fantastic bound for our error. We know that if you took S3, you're within 1/4 of the actual value to which the series converges. What would that look like if I drew it on here? Well, if I said at S3, you are within 1/4 of the actual value of the series, that means that, well, from here to here would be 1/4, but you're also saying like plus or minus. Remember that with error bounds, we don't really care about sign. And yes, I agree that this side is not as useful, but it surely is an easy way as a general rule of thumb to offer up an error bound, right? When you're at S4, If you used 4 terms, so say you used this many terms, so that means that you would say this is an approximation of the entire series. Your question is, what's the error bound now? Well, you know that 1/5, A5, that 5th term, adding it on would overshoot whatever you're converging to, but it would give you a totally valid error bound, in which case we would say, hey, the error bound, if we were just using the first 4 terms, would be 1/5. We're guaranteed that adding on 1/5 is going to ping pong us back over and we'll land on the other side of whatever we're converging to. So in that particular case, let me try to draw in purple here. Right, that's about 1/5. That'll give you a solid error bound if you're using S4. So if you have an approximation for this alternating series, say we're talking about S4, a complete sentence that would relate the alternating series to the error bound would say, if I use just the first 4 terms, 1 minus a half plus a third minus a fourth, just that finite sum, to approximate what this series converges to, I'm guaranteed to be within 1/5 of the actual value to which this series converges, right? If I add or subtract 1/5 from S4, it will create this lavender band here, and sure enough, the point of convergence lies in here. It is within this interval. And so the phrase that we use to describe this phenomenon is that an alternating series can be approximated by a finite sum, and the error bound for that finite sum is going to be the magnitude of the first unused term. Now that can sound a little weird because you're like, in a series, aren't you using all the terms? But remember, we're talking about, I'm only going to use an approximation. I'm only going to use a finite number of the terms of the series to say this is about how much this series adds up to. So in our particular case, the terms we would use in our approximation in that previous example I talked about when we were talking about S4, the terms we'd use would be the first 4 terms. The first unused term would be A5, or the 5th term, 1/5. And so that's how you end up with, if I'm using the first 4 terms as an approximation for this series, the error bound is going to be the magnitude of the 5th term. Let's put this to use and see how it works. Here's a typical question involving using a finite sum, or like the first part of a series, and figuring out how off are you from what the series converges to. It says, suppose you want to approximate cosine of 0.5 with error less than 0.0001. That's pretty small. It says, how many terms could you take to guarantee your error was small enough? Now there are a few things that you want to do to set yourself up first. The beginning, you want to just remind yourself what the Taylor series of cosine of x, not even cosine of 0.5 yet, just cosine of x looks like. And there it is. I've written out the first 4 terms and just sort of left the ... at the end there. You have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And now, of course, our question is, we want to use this to approximate cosine of 0.5. So for us to find a series that would converge to cosine of 0.5, we'd have to plug in 0.5 everywhere we see an x. Let's go ahead and do that now. All right, here it is. This is the series that we're looking for. It is converging to cosine of 0.5, and we want to know how many terms do we need to use. We're going to create a finite sum. Do we need like the first 2 terms, the first 3 terms, the first 4 terms, the first 5 terms? Before we're guaranteed that our error is less than 0.0001. Now, a few pro tips when dealing with things like this. First of all, it's much easier if you convert everything to fractions. So the first thing I want to convert to a fraction is what my error is up here. And so this is tenths, hundredths, thousandths, 10,000ths. So this is going to be, I want an error less than 1 over 10,000. And then I also need to work on this cosine of 0.5. I want to plug in 1/2 everywhere I see 0.5, just so it's a little bit easier for me to get a handle on the magnitude of these terms. Now, I added in an additional term at the end because I got a little nervous, to be honest with you. 1 over 10,000, that seems really small. Maybe I need to look at more and more terms. It seems like it would take a long time before an approximation would become that accurate. Now we want to think about, we're looking at a convergent series where the series is converging to cosine of 0.5. And what ends up happening is that with each successive term, we are moving from this side to this side, to this side, to this side. And so we're going to use the fact that when you're looking at partial sums, the magnitude of the first unused term, so if you're looking at the third partial sum, which is the sum of the first 3 terms, the magnitude of the fourth term would be a bound for your error. If you're looking at the fourth partial sum, right, the sum of the first 4 terms, the magnitude of the fifth term would be a bound for your error. So we need to figure out which of these has a magnitude that is less than 1 over 10,000. And we're going to say, excellent, if, the 10th term is magnitude less than 1 over 10,000, then we could use, right, the first 9 terms. And that 10th term will be the first unused term, and it will be our error bound. So let's take a look here. I know that this one's too big, right? 4 times 2, that's going to be an 1/8. Oh, man. Here, I know that this is really still too big because 2 to the 4th, that's going to be 16. And 4 factorial, that's going to be 24. And sorry, but 16 times 24 does not give me 10,000 there. But let's take a look at 2 to the 6th times 6 factorial. Right? Let's do a little computation on the side. Well, 2 to the 6th, right, is 64. And 6 factorial, well, that's pretty big. So let's take a look. I did some quick notes on the side, and you can even copy my approach to computing factorials when you're doing things by hand on an exam or something. I do 4 factorial by itself, and then I'm like times 5 times 6, and I am not signing up to do 24 times 5, and then that product times 6. You absolutely could, but that is more complicated than just saying this is the same as 24 times 30, which is 720. So what we actually have here in this term, 1, 2, 3, the 4th term, right, is 1 over, and you have 64 times 720. Now let's see how big 64 times 720 is. Now you could absolutely just multiply 64 times 720, but some people prefer to do a little bit of approximating. Well, note that if I made 64, if I bounded it below and I bounded 720 below into things that were much easier to multiply together, I would end up with something that has a smaller denominator and so would be bigger than the original 1 over 64 times 720. For example, 64, it's greater than 50. And 720, that's greater than 500. Right? So 64 times 720 would be greater than 50 times 500, which is 25,000. So I know that 1 over 64 times 720 is going to be, right, less than now 1 over 25,000. Right here we were just talking about the denominator, that 64 times 720 is going to be greater than 50 times 500. So 64 times 720 is going to be greater than 25,000, which means that if you have something greater than 25,000 in the denominator, it's going to be less than 1 over 25,000. And we also know that 1 over 25,000 is less than 1 over 10,000. That was our required bound, right? So we've shown that this term right here is less than 1 over 10,000. You absolutely could have just multiplied 64 by 720 and called it a day, and said, hey, that denominator is larger than 10,000, so it's going 1 over 64 times 720 is less than 1 over 10,000. But now, what are we saying by that? Well, we're saying that if this term right here is less than 1 over 10,000, this is going to be the error bound if we only used the first 3 terms. If we only use the first 3 terms, we could say this right here would be an upper bound for our error. And we want to do that, right? Because we know that this is actually less than 1 over 10,000. So if we use the first 3 terms, we'd be able to say, hey, using the first 3 terms guarantees that we're within 1 over 10,000 of our actual value. So if we wanted to approximate cosine 0.5 with this level of accuracy, we would only have to use these first 3 terms. We would say 1 minus 1 over 2 squared times 2 factorial plus 1 over 2 to the 4th times 4 factorial. And that would be an approximation that would get us as close as we needed to be.